just before we wind up, let's consider some practical aspects. Um, uh, in modeling and also interpreting an FEM simulation, finite element based uh, let's say problem. Okay, so as I mentioned before, there is no universal way uh, follow when we are solving a finite element simulation. Of course, when we use different elements, we followed certain steps in deriving and tackling a finite element simulation. That is fixed. No matter what or how complex the problem is, the same 7 or 8 odd steps which we followed, you will have to follow when you're solving a finite element simulation. That is true. But when it comes to practical aspects, uh, depending on the problem, you would have to apply your skills and your know-how depending on the problem or the complexity of the problem. So I will provide you some certain hints which might be really useful for you when you're tackling such problems. So especially when we are trying to tackle a finite elements based problems, uh, there are certain general recommendations with respect to the, let's say, mesh size and how many whether the mesh should be locally refined or not, and how the mesh, that is how the mesh should be when there are, let's say, uh, concentrated loads and where there's an uneven distribution of the material properties, let's say, or how to tackle or how to simplify a problem when there is symmetricity present, and how to tackle different boundary conditions, and whether we could really increase the number of nodes, use higher order shape functions to improve the results. There are certain aspects, different aspects, which we can consider when we're tackling a problem. And so some of the general, let's say, considerations that you have to take into account is you have to have a physical feeling as to what you are trying to model. For example, if you have a physical feeling as to what is the process behind you are trying to mimic or you are trying to simulate, then your intuition will help you to uh, develop a quite accurate model. So this finite element model is also known as kind of like an art, which is guided by physical interactions which takes place within this body uh, for a certain region which you are trying to model. So of course, with experience, you can learn different techniques and of course use these general purpose programs to tackle different problems. Uh, one of the most difficult tasks also in finite model element modeling is to identify the physical behavior or to understand the physical behavior of various, let's say, elements or various components of the problem that you're trying to tackle. So uh, what I'm trying to say is that a good understanding of the physical behavior will help you to select the proper element type, like, and the proper boundary conditions to simplify, let's say, the problems. For example, if we just think in terms of the elements, constant strain triangular elements and linear strain triangular elements. Now you as an engineer, you are given a bending problem. you are trying to develop a cantilever beam, of course, and which is subjected to, let's say, heavy loading, or let's say some kind of distributed load. Yeah, due to this distributed load, it will undergo certain deformation. So when you are given such a problem, of course, you can apply this beam theory, and you can apply analytically equations to get a exact solution for this problem. And if the things get more complicated, if there are certain, let's say, different materials used within this body, and if there are drastic changes in the loading conditions within the body, then at such locations, no, let me, yeah, let assume that there are drastic changes of the loading conditions within this element. Yeah, so this is subjected to two types of loading with different magnitudes. Yeah, and this is a bending problem, of course. Then you have to have an intuition as to what type of material you would use, what type of element you would use to model this finite element problem, and what would the mesh look like when you are developing such a problem. So whenever there are drastic changes in the loading conditions, then at certain locations you need to capture these changes, you need to introduce nodes. And if there are changes in the material in such places, you have to be particularly interested in about the mesh size as well as the nodes, and you use the proper elements at appropriate locations to tackle such problems. This is a bending problem, and since a bending problem, in order to accurately describe the bending problem, you need to use, let's say, linear strain triangular elements. If you are using a constant strain triangular elements, there can be deviations, but if you increase the mesh size, drastically increase the mesh size, you might be able to approach the, let's say, at least get close to the results obtained by, let's say, linear strain triangular elements. So such things have to be kind of like, there should be a feeling for this. It should be at your fingertips, they say, when you come to model such a problem. And if, of course, if you see a certain symmetricity, you can use this symmetricity to drastically reduce the computational time. Imagine you might be able to reduce the simulation time from, let's say, 2 days to, let's say, 1 or 2 hours, depending on how you simplify the problem. So in this context, one of the important aspect is, let's say, consideration is, let's say, the aspect ratio. Aspect ratio and element shapes. So we say, of course, the aspect ratio is defined by the ratio between the longest dimension of a certain element to the shortest dimension. So it is the general rule of thumb in FEM simulation that the aspect ratio should be closer to 1 as much as possible to improve the simulation results. Yeah, so of course you can use large elements having large aspect ratios like this, of course, this, depending on the problem, and which will also provide accurate results if there are no drastic changes in the problem. For example, if you're tackling a complex geometry, and if you see the variation of certain strain or stress within a certain boundary is constant, or there is no variation of stress within a certain region, then at such regions you can use elements having large aspect ratios. But whenever you need accurate results, you need to use as elements, of course, having somewhat small aspect ratios, meaning aspect ratios close to 1 would yield better results than the elements having large aspect ratios, of course, depending on the problem that you try to tackle. So for example, now if you are looking at a, let's say again, a bending problem, a beam, cantilever beam, which is subjected to, say, certain type of loading at the very end, you can use different type of elements. Yeah, you can use this type of elements having large aspect ratios, or you can use, let's say, elements having aspect ratios close to 1, or also maybe intermediate elements, let's say, for developing your mesh to tackle this problem. So based on the aspect ratio of the, let's say, different type of element you use, your results would vary. And since this is especially subjected to a parabolic road distribution, let's say if you assume a parabolic road distribution within a certain within one end, of course, then you see you require, let's say, elements having aspect ratios close to 1 to accurately capture this picture. So if you're interested, of course, maybe during the lab sessions, let's try to do this. We can change the aspect ratios of certain elements, and you can compare and plot the accuracy of the results which you would obtain when you're running a simulation. Yeah, so aspect ratio is an important aspect which you have to keep in mind when you're selecting the element. And of course, you need to think about, let's say, the symmetricity of the problems. I think you are aware of such issues. You by now, I think you, of course, you worked out a problem, a thin plate, plane stress problem, a thin plate with a hole in the middle. So in such cases, you probably you, of course, which is subjected to tensile forces. In such cases, I assume that you use the complete model in order to calculate the results, or in order to perform the simulation. If you are careful enough, you would be able to see a symmetricity of this problem, symmetricity into direction, and of course, you can use this symmetricity to let's say, to develop a model by applying, let's say, corresponding proper boundary conditions. We can apply, let's say, fixed boundary conditions at this location as well as this location to mimic the total system. And by applying such boundary conditions, you can simplify the problem and analyze only 1/4 of the problem, meaning the number of nodes and the elements, or of course the nodes, tend to approximately reduce by 1/4. So the computation time is drastically reduced by applying such symmetry, by applying symmetricity principles to reduce the problem. To simplify the problem. And of course, you need to think of, let's say, natural, let's say, discontinuities between different subsections. For example, let's say if you are, let's consider an arbitrary boundary. Yeah. Let's, yeah. So which is fixed at a certain in two sides, and you are interested in developing a mesh for this type of particular model, then because let's say um, on the fixed end you would like to use certain mesh model with a certain aspect ratio, and on when you move on to the right hand side, you would like to use a much more larger uh, let's say mesh size, since you assume that the stress variation in this region is quite insignificant, and you would like to use a much more, let's say, larger mesh or element size to tackle this problem. So you can see directly there's a transition between the different mesh sizes. That is, there's a transition from a smaller element size to a larger element size. In such cases, in order to make a continuous let's say transition between these two different mesh sizes, what would be required is, since this would be a drastic change from when we move from the left hand side, the smaller mesh size, to the larger mesh size, this has to be supported with uh, let's say triangles, continuous triangles, so that your simulation will be continuous. Of course, your mesh would be continuous and would be mm, compatible uh, without having large discontinuities, uh, which will might prone to errors or unrealistic deformations or displacements, unrealistic stress levels um, within this particular region. So you, in such places, you need to have natural subdivisions to tackle the discontinuities of the problem that you're trying to analyze, within the problem that you're trying to analyze. And more specifically, you can also apply, let's say, depending on the problem again, local refinements. If you see, as I mentioned before, a large stress variation or material change at a particular location, you can apply this local refinements and improve the mesh at the particular location where you would like to analyze in more detail, where you think that there will be an abrupt change in the geometry, or abrupt change in the material properties, or abrupt change in the distribution of load. Or in such cases, you could use the concept of the local refinements, changes in the geometry. When I mean changes, I mean drastic changes, changes in geometry. The term drastic depends on the type of the model, of course, that you are trying to tackle. So the changes in the material, if you're analyzing a composite material, then you need to do local refinement in this change. If there are changes in the boundary conditions or loading conditions, in such cases, you need to apply local refinements to improve the model. So, and there are different aspects, of course. These are some of the aspects which you would like to, which you would have to think about when you're performing or when you're tackling a model in FEM simulations. I will upload some of the supporting material which you can read into very details, which will also be quite useful in your lab sessions. And it's also important that you do a convergence test at the end of when you're presenting results. So it's not that you do a single simulation and in one go you obtain the results and you present the results. You need to see whether the residuals are converging. If not, your finite element simulation might have, or most likely is erroneous, meaning there can be local hotspot, concentrated hotspot, or there can be improper boundary conditions. Your mesh might have is might it might be the case your mesh has local um, stress concentration, so your mesh is invalid in certain locations. So residuals are important. You need to test this whether your solutions are converging. It's always nice to use different element sizes, elements having different aspect ratios, to see whether your the solutions converges when you use elements having different aspect ratios. You can change the number of elements, meaning the number of nodes, and see whether you get improved results. Of course, all these variations can be done once you get develop a certain model. And don't forget to compare your results using the analytical equations whenever there's a possibility to compare the results with the theory. Do so, because you get a approximation as to where you land with the results, finite element simulation based results. Okay, and these are some of the important considerations which might be useful when you're tackling plane stress and plane stress boundary conditions, or problems more specifically, because when you are dealing with 3D problems, and of course when you're using elements having large degrees of freedom and having higher order shape functions. So these are some of the important information I would like to mention. Do you and we have already come up to the session, at least I have come up to the session by which I intended to cover. Of course, there are so many other practical aspects, but this would be quite helpful for you to read and understand. And also you will understand more during the lab session, during the discussions which you will have with the instructors, how you can tackle different problems. And it's always better to learn by doing things, especially when it comes to simulations. The important thing is you do and learn, you might run into problems. The more problems you run into, the better, because it will help you in terms of the learning curve, uh, uh, and you will have more experience in finite element simulations. Of course, there's a lot of material covered in the lectures. This is the nature of this course. Take your time to go through the materials, and important thing is that the idea is not for you to memorize all these equations, but try to get the concept, what you will be applying, and try to relate the theory you learn during the lectures to the lab classes. This is the important link that I would like you to have at the end of these lessons, that you always link what you learned in the lectures to the simulation or the lab classes when you are tackling a problem. So it's really important to focus on these practical aspects. I will be testing about these practical aspects maybe in the end semester exams, as well as probably during a set of quizzes, which I also plan to conduct by simultaneously to the lab classes. So make sure you get familiarized or read these materials and get familiarized with these practical aspects. Okay, maybe I can stop the recording, since we have already come up to the end of the session. I will stop the recording.